discussing the frequency response analysis. Under frequency response analysis, today we will cover the construction of polar plot. Previously, we started the construction of Bode plot. Now, we will discuss the construction of polar plot. This plot is also called Nyquist plot because this plot is used for the stability analysis using Nyquist criteria. So, the polar plot is also called Nyquist plot. Now, a Nyquist plot is an alternative way of Bode plot to represent the frequency response characteristics of dynamic systems. Nyquist plot is an alternative way of Bode plot to represent the frequency response characteristics of a dynamic system. So, this is basically the alternative to Bode plot, and this can be used for stability analysis later. This plot is constructed using the transfer function in the complex plane. This plot is constructed using the transfer function in the complex plane. Fine. Now, we will take the transfer function in general form. I mean, we can take the transfer function as Gs. Now, replacing S by j omega, we can write as Gj omega, which is frequency response transfer function, and this we can write again in Cartesian form as real Gj omega plus j imaginary part fine. We can write the transfer function like this. Now, we will produce one plot in the complex plane. So, this is real axis, this is imaginary axis. And this is a unit circle which has the radius of 1. This is a unit circle. Fine. That means this point corresponds to 1 0. This is the origin, and this point corresponds to -1 0. This one -1 0, this is 1 0, and this is the origin. Now, from the frequency response transfer function, we can write the expression for amplitude ratio. Amplitude ratio is root over of the real part whole square plus imaginary part whole square. Fine. Amplitude ratio we know is represented by output amplitude divided by the input amplitude. I mean amplitude of the output divided by amplitude of input, and this transfer function Gs, which is represented as output divided by input. Agree? Here what is the amplitude of Fs? 1, because we can write this term divided by 1. I can write this term divided by 1 plus j multiplied by 0. That means amplitude of output is this, amplitude of input is 1. Agree? So, we can say that here amplitude ratio is becoming output amplitude. Now, what will be phase shift? Phi. Phi we can write as tan inverse imaginary part divided by the real part. Fine. If we consider this as a complex number, then suppose this part O B represents the real part, B A represents the imaginary part. So, how much is OA? OA is the amplitude ratio. Agree? If we consider Gs is this one and amplitude ratio is this one, square root of real part square plus imaginary part square, then this OA represents the amplitude ratio. So, I can write this amplitude ratio is basically OA. Then this is basically the magnitude of this Zj omega. How much is argument? Argument is this one phi, that means this angle is phi. Agree? This angle is phi and this OA is representing the amplitude ratio. So, this is the polar plot of the transfer function Gs. So, this is the polar plot of the transfer function Gs. Next, we will discuss the construction of polar plot for first order system, second order system, etc. So, in the next we will consider the first order system, I mean the construction of polar plot and we will consider first order system. The transfer function of a first order system we can write as k divided by tau s plus 1. Fine. This is the transfer function of a first order system. We determine the expression for amplitude ratio, that is k divided by root over of tau square omega square plus 1. We determine the expression for phase angle phi, that is tan inverse minus tau omega. These two expressions we determined earlier. Now, we will consider both the process gain and time constant are equal to 1. We will consider both k and tau are equal to 1. Fine. Now, the Bode plots, the polar plot starts at omega equal to 0. Fine. The polar plot starts at omega equal to 0. If we consider omega equal to 0, what is amplitude ratio? I mean, how much is amplitude ratio? Amplitude ratio is 1. How much is phi? Phi is 0. Fine. So, if we consider this point, I mean omega equals 0, what will be the polar plot? This is real axis, this is imaginary axis. So, first we will draw the unit circle. This is the unit circle. Amplitude ratio 1 means this is basically 1, I mean this point represents 1. Agree? When phi is equal to 0. So, amplitude ratio 1 and phi equal to 0 represent this point. Agree? So, we will write here when omega equal to 0, the starting point we get this one. Next, we will consider the end point. The plot terminates at omega equals infinity. Plot terminates when omega is equal to infinity. If omega is equal to infinity, how much is amplitude ratio? Amplitude ratio is 0. How much is phi? Phi is minus 90 degree. Fine, because phi is minus tan inverse tau omega. So, can we locate the end point? End point is this one. Here phi is equal to minus 90 and amplitude ratio 0. So, this is the end point. Next, we need to consider the intermediate points to draw this polar plot. Now, when omega is in between 0 and infinity, how much will be amplitude ratio? When we considered omega 0, we got amplitude ratio 1. When we considered infinity, we got amplitude ratio 0. So, we can write like this. Agree? When we considered omega 0, we obtain amplitude ratio 1. When we consider omega infinity, we obtain amplitude ratio 0. So, we can write this accordingly. Similarly, we can write for phi. When omega is 0, phi is 0. When omega is infinity, phi is minus 90 degree. So, we can write this 0 greater than phi greater than minus 90. If we use intermediate points in this complex plane, then we will get the polar plot like this, and this is the direction. This is the starting point, this is the end point, and we need to take few intermediate points. Then we will get this type of plot. So, this is the polar plot for the example first order system. This is the polar plot of the example first order system. Fine. Similarly, we will try to construct the polar plot for second order system in the next. Polar plot second order system. For the second order system, we know the transfer function is represented in general form as say k divided by tau square a square plus 2 zeta tau s plus 1. This is the transfer function of a second order system. Fine. Previously, we determined the expression for amplitude ratio and phi for second order system. Their amplitude ratio equals k divided by root over of 1 minus tau square omega square whole square plus 2 zeta tau omega whole square. This expression we determined earlier. Similarly, we determine the expression for phi as tan inverse minus 2 zeta tau omega divided by 1 minus tau square omega square. Fine. Now, we will construct the polar plot, and for that we will consider k and tau both are equal to 1. For simplicity, we are considering the k and tau equal to 1. Now, the polar plot starts at omega equal to 0. So, plot starts at omega equal to 0. What is the corresponding amplitude ratio? 1. How much is phi? Phi is 0. When omega is equal to 0, amplitude ratio becomes 1 and phi becomes 0. Now, we will locate the starting point in the complex plane. This is the unit circle. When amplitude ratio is equal to 1 and phi is equal to 0, we get this point. So, when omega is equal to 0, the polar plot should start from this point. Secondly, we will consider we will try to find the end point. This polar plot terminates at omega is equal to infinity. Now, if this is the case, then how much is amplitude ratio? 0. How much is phi? Phi is minus 180. Phi we can write as tan inverse 2 zeta by tau omega. Tan inverse 0 and this we consider minus 180. So, what will be the end point in this complex plane? Here, but the polar plot should go through this quadrant. Next, we need to generate some intermediate data. See, here another parameter is involved, that is zeta. Fine. So, when zeta is greater than or equal to 1, amplitude ratio becomes less than or equal to 1. It is easy to test that when we consider zeta is greater than or equal to 1, the amplitude ratio becomes less than or equal to 1. What it indicates? The polar plot will be within the unit circle. Amplitude ratio less than 1 means the polar plot should be within the unit circle. Similarly, if we consider zeta less than 1, it is easy to investigate that amplitude ratio becomes greater than 1. When zeta is less than 1, amplitude ratio becomes greater than 1. That means, this is outside of the unit circle. The polar plot goes outside of the unit circle. So, this is when omega equals infinity, this point when omega equals 0. So, when zeta greater than 1, we obtain this plot, because it is within the unit circle. This we obtain when zeta greater than 1. Similarly, when zeta less than 1, we obtain this plot. I mean, this polar plot is outside of the unit circle. Fine. So, it is clear that the polar plot depends on the value of zeta. This is the polar plot of the example second order system. Fine. Next, we will consider the third order system, construction of polar plot for a third order system. The transfer function of a third order system can be written as 1 divided by tau 1 s plus 1, tau 2 s plus 1, tau 3 s plus 1. Fine. This is the transfer function of a third order system. Now, it is easy to show that when omega equal to 0, amplitude ratio is 1 and phi is 0 degree. It is easy to show that when omega equal to 0, amplitude ratio becomes 1 and phi becomes 0. Similarly, when omega tends to infinity, amplitude ratio tends to 0 and phi tends to minus 270 degree. For the first order system, we obtain minus 90, for second order system minus 180 and for third order system minus 270. Fine. Similarly, we can generate some intermediate data. This is a unit circle in the complex plane. Starting point is this one and end point is this one, and the polar plot we obtain like this. So, this is the polar plot of the example third order system. Fine. This is the polar plot of a third order system. We can take another example like a pure delay system, how we can construct the polar plot of a pure date time. The transfer function of this element, pure date time element, we can write as exponential minus TDS. This is the transfer function of the pure time delay system. How much is amplitude ratio? You can compare this with the standard polar form, that is amplitude ratio exponential of j phi. Compare this with this. How much is amplitude ratio? 1. How much is phi? Minus TD omega. Fine, minus TD omega. So, it is obvious that amplitude ratio is independent of omega. It is obvious that amplitude ratio is independent of omega, and that is always 1. So, the polar plot is a circle of radius 1. It clearly indicates that the polar plot should be a circle of radius 1. So, polar plot is a circle of radius 1. This is real axis, this is imaginary axis. Amplitude ratio 1 means the polar plot, this is the polar plot, you can say. The polar plot is a circle of radius 1. As omega increases, what happens? As omega increases, this will start rotating. It is obvious from this expression. If you keep on increasing the omega value, you will see that this phi will changing like this. That means, as omega increases, this will start rotating. Now, next question is, what is the direction of that rotation? I mean, we have to show the direction of this polar plot also, that will be clockwise. So, direction of rotation be clockwise. Direction of rotation will be clockwise, clockwise rotation. So, this is the polar plot of the pure date time system. Now, what is the purpose of this frequency response analysis studied so far? What is the purpose of this frequency response analysis? So far we have studied under frequency response analysis the determination of amplitude ratio and phi. So far we have studied under frequency response analysis the determination of amplitude ratio and phi. We have studied the construction of Bode plot. we have started the construction of polar plot. But what is the purpose of doing all this? What is the purpose of doing all these? The frequency response analysis is performed for two reasons. One is for stability analysis, another one is for controller tuning. The frequency response analysis is performed for two reasons. One is for stability analysis of the closed loop system. Frequency response analysis is performed for tuning of control parameters. Tuning of control parameters. And it is interesting to note that for the stability analysis and for controller tuning, we will use this Bode plot and polar plot. So far we have just started the construction of those plots. In the next we will use those plots for stability analysis and for controller tuning. So first we will discuss the Bode stability criteria, and we will use for that purpose the Bode plot. So first we will discuss the Bodev stability criteria. Fine. Now for this purpose we will consider one closed loop system, because it is mentioned that the Bode stability criteria is used for stability analysis of the closed loop system. So we will consider a closed loop system, and presently we are making that closed loop block diagram having a P only controller, then considering ZF equals 1, and GP equals exponential of minus 0.123 s divided by 0.1 s plus 1 and considering Gm equals 1. Fine. This is the closed loop block diagram of a servo problem. This is the closed loop block diagram of a servo problem. Fine. Now, you know that for constructing the Bode plot, we need the expression for amplitude ratio and we need the expression for phi. For constructing the Bode plot, we need the expression for amplitude ratio and phi. Now, for deriving the expression for amplitude ratio and phi, what we need? We need the open loop transfer function. Open loop transfer function we denote by z suffix OL, which is nothing but the multiplication of all 4 transfer functions GC, GP, GF, GM. Now, all the transfer functions are defined in this closed loop block diagram. Accordingly, we obtain Kc exponential of minus 0.123 s divided by 0.1 s plus 1. Agree? Now, we can write it like this: Kc divided by 0.1 s plus 1 and separately this exponential term. So, this is the transfer function of a first order system and this is a date time part. In the next, we will try to find the expression for phase angle phi. So, if we consider first order system and date time element, then we can write as phi equals phi 1 plus phi 2. This is representing the first system, I mean 1, and this is the second. So, how much this will be? For a first order system, we know phi is tan inverse minus tau omega. So, tan inverse, how much is tau? 0.1 omega. Fine. And how much is phi for this date time element? Minus 0.123 omega. Say this is in degrees, this is in radian. So, we will multiply this with 180 degree divided by phi. Definitely, if we write in the right hand side minus 180 degree, you can write here minus pi also. Accordingly, you write the left hand side. Presently, we are representing all in degrees. Fine. Can you calculate from this expression the value of omega? We are considering phi is minus 180 degree. Now, we will calculate from this the value of omega, that we obtain 17 radian per minute. The value of omega at phi equals minus 180 degree is called crossover frequency. The frequency which is calculated at phi equal to minus 180 degree, that omega is called crossover frequency, and which is represented by omega suffix CO. Crossover frequency. This is also called as critical frequency. The frequency which is calculated at phi equals minus 180 degree is called crossover frequency or critical frequency. Now, if phi is always greater than minus 180 degree, then there is no chance of instability. If phi is always greater than minus 180 degree, then there is no chance of instability, no chance of instability. Only when phi is less than minus 180 degree, then there is a probability of instability. I mean, that is unstable system. Therefore, we can say that phi equals minus 180 degree, that is critical value. Fine. So, we got crossover frequency equal to 17 radian per minute. Here the dead time is given in minute and time constant is also in minute. How we can calculate the amplitude ratio? If we consider the first order system and the dead time system, that means there are two systems. So, we can write the overall amplitude ratio equal to the multiplication of two individual amplitude ratios. For the first order system, we know the amplitude ratio is written as process gain divided by tau square omega square plus 1. This is the amplitude ratio for a first order system, and for the time delay system amplitude ratio is 1. Now, we will try to determine the value of this overall amplitude ratio at crossover frequency. Tau is 0.1. Crossover frequency we determined 17. Accordingly, we obtain this. Now, we obtain amplitude ratio equal to 1 when Kc equal to 2. I mean, if we write this amplitude ratio by Kc, we obtain 0.5. Fine. Amplitude ratio is this. Now, calculating this denominator, we can write amplitude ratio by Kc equal to 0.5. Then we can say that we obtain amplitude ratio equal to 1 when Kc is equal to 2. Fine. In this line, we can say that amplitude ratio is greater than 1 when Kc is greater than 2. You can conclude from this expression. Amplitude ratio becomes greater than 1 when Kc is greater than 2. Similarly, we can write amplitude ratio less than 1 when Kc is less than 2. Fine. Can we draw the Bode plot now? We will construct the Bode plot based on this information. This is omega, phi, omega, amplitude ratio. This is a log plot and this is a semi log plot. this is 0 degree. Now, at phi equals minus 180 degree, we obtain the omega, which is omega CO. This is crossover frequency. The frequency at phi equals minus 180 is crossover frequency, and this we obtain 17 radian per minute, correct. Now, this is the plot when Kc equal to 2. At crossover frequency, how much is amplitude ratio? 1, definitely when Kc is equal to 2. Agree? See, the definition, I mean, we have defined the crossover frequency as we consider phi equals minus 180 degree, we obtain this. Now, we have obtained amplitude ratio 1 when Kc is 2 at crossover frequency. We obtain amplitude ratio 1 when Kc equal to 2 and omega equal to omega CO. Therefore, we have drawn this, I mean, this is 1 at crossover frequency when Kc is equal to 2. When Kc is greater than 2, this is indicating Kc greater than 2. How much will be amplitude ratio? Greater than 1, it is clearly indicating that. When Kc is less than 2, how much is amplitude ratio? Less than 1. Fine. So, this is phi versus log omega plot. At phi equals minus 180 degree, we obtain crossover frequency, that is minus that is 17 radian per minute. Amplitude ratio is equal to 1 when Kc is equal to 2 at omega CO, that is shown here. Other two cases are also shown here. They are Kc less than 2 and Kc greater than 2. It is obvious from this plot that when Kc less than 2, amplitude ratio becomes less than 1, and when Kc greater than 2, amplitude ratio becomes greater than 1. So, this is the Bode plot. So, in the next day we will discuss the stability criteria, continuing this portion. Thank you. I hope presently what we are discussing, that is the most difficult part of process control. So, do not sleep sitting in the first bench.